Hello and welcome to this Revision Monkey video on what's going to be in the Separate Chemistry Paper 2 exam. If you're a separate scientist or a triple scientist, as you may be called in your school, you are those that study extra content with papers of 1 hour and 45 minutes long. And this video is for the AQA specification. Let's run through what to expect on the Chemistry Paper 2. I'll do a quick recap of evaluate, explain and compare questions. We'll have a look at calculations that you need to know because 20% of the paper will still be calculations. And we'll have a look at required practicals, which are 15% of the exam. And don't forget also lots of skills that we've covered before, things such as surface area to volume ratio, uncertainty, averages, including mean, median, mode, and tables and graphs are likely to come up as well. So have a look through the previous videos in paper 1 for those skills as well. Quick recap of what evaluate questions want you to do. They want you to give advantages, disadvantages and a justified conclusion to your answer. So these are often between 4 and 6 marks. So they won't tell you that, they just have the word evaluate. So you need to remember to put pros and cons of each thing and give your reason as to which is best and why. For compare, again, it won't tell you, but it expects you to write similarities between two things as well as differences. And also explain questions. They want you to say why, so include as much scientific detail as possible when you're answering explain questions. So let's have a look at calculations. 20% of the exam is calculations, as well as things such as percentages and mean, median, mode, etc. You may also encounter some of the C3 unit calculations that you normally get on paper 1. So having a look at our equations for paper 1 again, things such as moles equals mass over mR, concentration equals mass over volume, concentration is equal to moles over volume, volume equals mass over mR times 24, and the atom economy equation, and again on any paper expect that uncertainty to come up. Also remembering to convert from centimetres cubed to decimeters cubed for a volume, you divide by 1,000. So if the equation's got volume in and they give it to you in centimetres cubed, divide it by 1,000 first of all. So the ones to really focus on for paper 2 are these ones here, the moles and the concentration equations. It's unlikely that atom economy would come up again. Volume equation might come up for separate, but the three in the box there are really the ones that often transfer between paper 1 and paper 2. The required practicals that you need to be aware of are the analysis and purification of water, paper chromatography, rates of reaction, and the separate only practical, which is identifying ions.
Paper chromatography required practical. We use paper chromatography to separate coloured substances. So in this practical, you may be asked a question similar to the one above that says, do food dyes A and B contain chemicals that are in band dye X? So in this practical, we're going to separate 3 dyes, A, B, and another one called X, and we're going to compare the patterns at the end of the practical. In your exam, they might not talk about food dyes, they might be talking about inks or another random coloured substance, but the process is exactly the same. What you need to do to start off with is draw a horizontal pencil line around 2 centimetres from the bottom of a piece of chromatography paper. Do not use pen, as this will smudge and spread up the paper. Pencil is insoluble, so will not dissolve in the solvent. So this line here that we draw on must be drawn in pencil. On the pencil line, put a small dot of the dyes that you want to separate and label these with pencil underneath. So I've labelled them A, B and X. Place the chromatography paper in a solvent, for example water. The solvent must be below the pencil line. Put it in a beaker with a lid to prevent the solvent from evaporating. Then we leave until the solvent front nearly reaches the top of the paper, then remove the chromatography paper and leave to dry. So the process of separating a substance through chromatography has 2 different stages. The paper itself is called the stationary phase, and when the inks are dissolved in the solvent, that is called the mobile phase. And within the inks that you've put on the paper, you will have different compounds, and they will interact differently with the paper, and they will have different solubilities. So they will spend different times attached to the paper in the stationary phase and different amounts of times dissolved in the solvent in the mobile phase. So you'll end up separating the substance as it moves up the paper. And to do that, what happens is the solvent moves up the paper, and when it hits the dyes, it dissolves any of the soluble compounds in the dyes. They will then be carried up the paper in the mobile phase, and depending on their solubility, they will stop at different distances up the paper. I mentioned earlier the solvent front. That is where the solvent finishes as it goes up the paper. So if the solvent is moving up and it gets close to the top of the paper, where it reaches here is called the solvent front, and when it gets near to the top, we will then remove the paper and leave it to dry. So the pattern left on the chromatography paper is called a chromatogram. So after we've left it to dry, we will see several dots of different colours on the piece of paper. We would then compare the chromatograms of dyes A and B with the chromatogram of the band dye X. In your exam, you're likely to see a chromatogram in black and white like this, rather than it being printed in colour, and each dot just shows how one of the colours is separated as it's gone up the page. So you can see here dye A has 2 dots and so has dye X, and this top dot here is in exactly the same position as the one on X, suggesting it could be the same compound. Now you'd want to investigate this further to see if dye A does contain one of the chemicals that is in the banned food dye X. Because we've only tested this so far on one solvent, we chose the solvent as water. But to be absolutely sure that our food dye contains a banned chemical, we would need to repeat this in different solvents, for example maybe ethanol. And if this compound in A matched X in different solvents, it's highly likely that it is containing that banned compound. We can't just be sure if we just use one solvent. We must repeat it with different solvents to be absolutely sure. In different solvents, different compounds will spend different amounts of time in the mobile and stationary phases, and what we'll talk about later is the fact that they can have different RF values. The position of this colour on dye A does not match that of dye X, and you can see for dye B it only has one colour here, and it doesn't match at all with dye X. Now because dye B's got one colour and one colour only, this tells us that dye B is a pure substance because it only contains one compound. In the exam you might be asked to calculate an RF value. You do this by calculating the distance travelled by a substance divided by the distance travelled by the solvent. This top line here is representing the solvent front, which is where the solvent got to before we took the paper out of the beaker. And I'm just going to show you an example using one compound here that we found on our chromatogram. Now the important thing is when you're calculating the RF values, you must calculate it from the centre of the dot on your chromatography paper. Not at the top, not at the bottom, but right in the middle of the dot that you're using. And the baseline that we're using is our pencil line where the dye started. So we need to measure the distance travelled by the substance, so this distance here, and then the distance travelled by the solvent. So let's say, for example, the distance travelled by the substance was 400 millimetres and the distance travelled by the solvent was 500 millimetres. Then we do 400 divided by 500 to get us an RF value of 0.8. As I alluded to previously, RF value will be different depending on the solvent used. So this could be, for example, the RF value for water for this particular compound, but if the solvent was ethanol, then this number here would be different. Rates of reaction required practical. When wanting to calculate the rate of a reaction, you might need to use one of these two equations. The first one says the rate of reaction can be calculated by the amount of reactant used up over time, and the second one is the amount of product made over time. So we're going to design some investigations using these two equations. Now there are several factors that you may be asked about in the exam that affect the rate of reaction. Those include temperature, concentration, and surface area. So you may well be designing an experiment and changing any one of these three things. So that would be your independent variable. And if you change temperature, for example, you need to keep concentration and surface area of your reactants the same. And the same goes if you are selecting a different independent variable. One of them you change and the other two you have to keep the same. There are several different practicals that you can do to calculate rate of reaction, and any one of these may come up in the exam. So this first one focuses on the amount of product made over time, and the independent variable that we're going to change is concentration. So we'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour it into a conical flask. We'd place, for example, 1 centimetre of magnesium into the conical flask, attach a gas syringe and start a timer. So in here we'd have our acid and our piece of magnesium, which you should know is going to create hydrogen gas. To calculate the rate of reaction in this experiment, we could record the volume of gas produced at regular intervals, for example, every 30 seconds for 5 minutes. And as gas is produced by the reaction, the gas syringe will move outwards and you can measure the volume of gas produced. Do not write amount, you must use the word volume. Then we would plot the volume of gas produced against time on a graph, and we can use this to calculate the mean rate of reaction, and I'll go through how we do this later on. We then repeat the experiment for the following concentrations of acid. So this will be our independent variable, the concentrations of acid. The dependent variable would be our volume of gas, which we then turn into our rate of reaction down here. And important control variables are things such as the volume of acid that we are using, the length of magnesium that we're using, and things such as temperature as well. As in all experiments, it's also really important to talk about the fact that you're going to repeat the experiment 3 times and calculate a mean for each concentration of acid that you're using. So a different practical setup now, but still looking at how concentration affects the rate of reaction. This time, this focuses on the equation the amount of reactant used over time. So we start off by placing a conical flask on a balance and zeroing the balance. We would then measure 50 ml of 0.1 molar hydrochloric acid and pour this into the conical flask. And we then place 1 centimetre of magnesium into the conical flask and start a timer. We take the initial reading on the balance as well, so we're starting off with a mass of 25 grams. Now again, we're using magnesium and acid, so we're producing a gas, and because we have no bung on the conical flask, that gas is going to be allowed to escape out of the conical flask. And in doing so, because mass is escaping from the system, the reading on the balance is going to go down. So to calculate the rate of reaction, we can record the mass on the balance every 30 seconds. So we'd wait 30 seconds, write down the new mass, another 30 seconds, again writing down the mass, and so on, and so on. And then we plot the mass against time on a graph, and we can calculate the mean rate of reaction. We'd repeat this experiment for the following concentrations of acid: 0.5 molar, 0.7 molar, and 1 molar, and as always is good practice, right at the end that you're going to repeat it 3 times for each concentration and calculate a mean. A third practical that you might see in your exam, again answering the same question, we're changing concentration and measuring the rate of reaction, is when you draw a black cross on a white tile or piece of paper and place a conical flask on top. we'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour that into the flask. And we'd also measure 50 ml of sodium thiosulfate using a measuring cylinder and pour that in the flask as well. So you can see at the moment when we've put the acid and sodium thiosulfate in, we can still see the cross because the solution is colourless. However, gradually over time, a precipitate will form to make the solution go cloudy, and at that point we will no longer be able to see the cross. So you can see now, when the solution has gone cloudy, we can no longer see the cross, and we then record the time it takes for the cross to completely disappear. Obviously this is subject to error because different humans will have a different opinion on the exact time that the cross has disappeared. We'd repeat the experiment for the following concentrations of acid: 0.5, 0.75 and 1 molar. And for this one, because we're not measuring the amount of reactant used or the amount of product made over time, we're simply looking for the time it takes for a colour change. We could use the equation rate equals 1000 divided by time to calculate a rate of reaction for each concentration that we're using. So with the results of a rate of reaction experiment, you may well be asked to draw a graph or do some calculations using a graph that's provided to you. So let's look at this graph here first of all. This might be a graph that we might have drawn from the first experiment, whereby we're measuring the volume of gas produced over time. A few things about rate of reaction graphs to start off with then. The steeper the gradient, the faster the rate of reaction. So you can see this first section here is really steep. Then a shallower gradient here, so the rate of reaction is slowing down. And at this point here, where the graph starts to level out, the reaction has actually stopped. And we know that because if you read off the graph here, no more gas is being produced. So here are some common questions that you're asked. One here says, what is the mean rate of reaction? So to calculate this from the graph, you would find out the point where the reaction stopped, draw a line from the x-axis up to that point, and then a line across to the y-axis. And you would read off from the bottom the time that it took, so 15 seconds, because from 0 to here is 15 seconds, and the volume of gas produced in that time, from the 0 up to here, so 34 approximately. And then we would calculate that by doing 34 divided by 15, giving us an answer of 2.3 centimetres cubed per second. We always do the y divided by the x in our calculations, and we get the units for rate by reading them off the graph. Centimetres cubed divided by seconds is what we've done, so those are our units. They could also ask for a mean rate of reaction for a particular time point. For example, what is the mean rate of reaction between 4 and 12 seconds? And in that case, at time point 4, you draw a dotted line up and across to the y-axis. You do the same for 12, and then you would read off between those two sections. So between 4 and 12, we've got a time of 8 seconds. And between our two markers on the y-axis here, we have a volume of gas produced of 12.5 centimetres cubed. So to calculate the rate of reaction, again, we do the y divided by the x. So our y value is our 12.5 divided by our x value of 8 seconds. 12.5 divided by 8 gives us, for that section of the graph, a mean rate of reaction of 1.6 centimetres cubed per second. And finally, a calculation for higher tier only. This one says, what is the rate of reaction at 8 seconds? So this is exactly at this time point here, what is the rate of reaction? And to do that, you need to draw a tangent on your graph, which is a straight line as close to the line as possible at that point, like the one I've just drawn on there. Now there will be some leeway in your exam, but try and get it as close as possible and following the same pattern as closely as you can. And then look on your gradient line where the line crosses the grid at some sensible points. For example, here it crosses in the corner and down here. Then we draw dotted lines to make a triangle between those two, And again, we're going to do the change in y, which is this bit, divided by the change in x to calculate our gradient. So we do 15 divided by 10 to calculate the rate of reaction at that exact point as 1.5 centimetres cubed per second. Analysing and purifying water required practical. For this practical, there are 3 different things that you might be asked to write about. The first one is testing the pH of water samples to see if they are in the potable range. The second one is to test the water samples for dissolved solids. Do they have a low enough amount of dissolved salt to make them potable? And finally, if they are not potable, how can we use distillation to purify the water sample? So the first 2 relate to analysing the water, and then the distillation refers to purifying the water. So looking at the first step then, testing the pH of water samples, we would use a device called a pH meter, or sometimes you may see it called a pH probe, but a pH meter is best. All you do with the pH meter is put it in your sample, and then it will give you a reading of the pH digitally. So I've got 3 different samples here. I've got some rainwater, some spring water and some seawater. And I put my pH probe in the rainwater, and I would then record the pH in the table. Repeat that with spring water and record the pH, and finally with seawater and record the pH. Now, are they in the potable range is the question that we're looking at. Are these safe to drink? Well, the potable range is between pH 6.5 and 8.5. So you can see here that the spring water and the seawater in these examples are within that pH range, so they could be potable, but the rainwater is too acidic. Okay, it falls below that pH range, so it is not considered to be safe to drink. But we don't yet know if it's potable or not, because it also has to have a low enough amount of dissolved salts and, of course, a low enough amount of microbes. The second part is then testing the water samples for dissolved solids. So we're going to look if they have a low enough amount of dissolved salt to make them potable. This is the equipment that we are going to use. We have a balance here. We've got our Bunsen burner on a heatproof mat with a tripod and gauze. And then we have a beaker, and this beaker is just acting as a water bath. It's just full up with tap water, and on top of that you've got an evaporating dish, and that is where you are going to put your water sample in your evaporating dish. All this water is doing is just acting as a water bath that will gently heat the evaporating dish. It's much better and much safer to do it this way rather than putting the evaporating dish straight upon the gauze. You can also get electronic water baths that will do this as well, which you may see in an exam. So the method for this, we are testing to see if this water sample has dissolved solids in it. So we're going to record the mass, hence the balance, of an empty evaporating dish. We are then going to measure 5 millilitres of one of the water samples, for example rainwater, using a measuring cylinder, and add this to the evaporating dish. So we pop our small amount of water in our evaporating dish like so. We then heat gently over a water bath until all the water evaporates from the evaporating dish. Now, to do it safely in the lab, what you might do is allow most of the water to evaporate and then leave the rest to evaporate slowly. But once the water evaporates, you'll be left with none in your evaporating dish. And you will allow that to cool and then reweigh the evaporating dish. You would then record any mass change of the evaporating dish, if there is any, and observe any salts left on the evaporating dish. So once the water had evaporated, if your sample contains salts, it would likely that you would see salt deposits building up on the sides of the evaporating dish. So when you were to put that dish back on the balance and reweigh it, you'd expect it to be heavier because it now has salt on it. You would then repeat steps 1 to 6 with the other water samples, for example if we used salt water and spring water. So when you look at your results, Just because one of the samples may have a low amount of dissolved solids, a low amount of dissolved salt in this case that we're looking at, it might not mean that it is still potable, even if it passes the pH test and the low amount of solids. You would have to make sure that it has a low enough amount of dissolved microbes. So if your water samples are not potable, you can use a process called distillation to purify the water sample. I've just used a different colour here just so we can make it obvious, but let's suggest that in here we put our salt water, because this is what many countries, such as Saudi Arabia, would do because they don't have much rainwater. And this will allow them to access drinking water from their normally non-potable salt water. So the flask that we put this in is called a round bottom flask, and you would heat that flask normally using a water bath or perhaps using a Bunsen burner if you're doing it in the lab. You have a thermometer at the top here, which you'd want to make sure for pure water was reading 100 degrees C, so that you know that in your beaker over here you are getting pure water. So as you heat the salt water, the water will evaporate and it should leave any salts behind in the round bottom flask. The water will evaporate and it will turn into water vapour and it will go up the tube here. This piece of equipment here is called the condenser, or you might see it written as the condensing tube. So the condenser is kept cold by this cold water going in and around the glassware. It doesn't mix with what's in the middle, it just goes around the glassware to keep it cool. And as the water vapour comes in here, it is then condensed into a liquid and then it will collect as pure water in the beaker. So in this purification process, we would test the pH of the water using a pH meter. We would neutralise it if we needed to by adding alkali if it's acidic or adding acid if it's an alkali. And we use a pH meter, not an indicator, to determine when it's neutral. Because if you're trying to purify a sample, there's no point adding an indicator like universal indicator in there because you're just contaminating it. And a pH meter is going to give you a much more accurate result. So then we pour the salty water into the distillation apparatus, and we said specifically it's the round bottom flask it goes in, and we heat it. And the distillation process, as discussed, will leave us with pure water in our beaker, and we would then just retest the pH at the end to check that it is neutral. If you're doing separate science, there could be an addition to this practical whereby you have to test the water for salt as well before you start. Now salt is sodium chloride, so this links into the last required practical that we'll talk about in testing for ions. Because if we wanted to test the water for salt to start with, we'd need to test the positive ion, which is sodium, and the negative ion, which is chloride. So to test for sodium, we would take a small sample and do a flame test, and a yellow flame will indicate the presence of sodium ions. And for the chloride ions, we would test for chloride ions by taking a sample and adding a few drops of dilute nitric acid and silver nitrate solution. A white precipitate forming would indicate the presence of chloride ions. So this, in addition, I would recommend you write about doing before and after the distillation of salty water. Identifying ions required practical for separate science only. In this required practical, there are lots of different tests to remember for different ions. So why would we need to test for ions? Well, if we had this unknown compound here, we would be able to do a variety of tests to identify exactly what that compound was made of. So this is the type of question you might be asked. Describe the test you would carry out to identify the ionic compound. Remembering back from paper 1, ionic compounds are metals and non-metals bonded together. So for example, you could have calcium sulfate. Calcium ions are the metal bonding with the sulfate ions. You could have sodium chloride, or magnesium carbonate, magnesium bromide, potassium iodide, or copper sulfate. So there's so many different ones that you could have, and these are just a few examples. With this compound, we have no idea, apart from the fact that it's white, we have no idea what it's made up of. So you're going to have to do a variety of tests to work out what the positive ion is, and we call this the cation, and what the negative ion is, and we call this the anion. Once you've worked out what both things are, you can then name the compound. So first of all, let's go through the test for cations, which are the positive ions. One thing that you can do to test for the metal ions, which are the positive ions, is to do flame tests. You'd need a wire loop made of an unreactive metal, for example platinum, and you'd need to clean the loop by dipping it in dilute hydrochloric acid and then putting it in a blue flame until it burns without any colour. You then allow the wire to cool and then dip it in the sample that you are testing, for example the white powder from the previous page. You'd then put your loop with your unknown sample back into a blue flame. If the flame was orange-red in colour, that would indicate the metal ion was calcium. If the flame was yellow, that indicates sodium. If the flame was crimson, that would indicate lithium. A lilac flame would show you'd have potassium, and a green flame would show you that the cation was copper. Flame tests, however, are not the only test that can be used to identify cations. There is another test whereby you add sodium hydroxide to your unknown ionic compound. So we've got a conical flask here, or can you use a beaker or a test tube, and you have sodium hydroxide and your unknown powder inside. A precipitate will form, and that's because you will make an insoluble hydroxide. So precipitate is a solid that's suspended in the solution because this hydroxide does not dissolve. The colour of the precipitate will then help you identify the cation. If a blue precipitate forms when you add sodium hydroxide, you have identified copper in the compound. If a green precipitate forms, you've identified iron 2, and the 2 just means you're talking about Fe2+, remembering that transition metals can make ions with different charges, because Fe3+, or iron 3, makes a different coloured precipitate. So iron 2 makes green and iron 3 makes brown. Now, if you remember that transition metals form coloured compound, which is content for paper 1 especially, then you'll remember that all the ones that are coloured are transition metals. So copper blue, iron 2 green and iron 3 brown. If, however, your unknown compound contains calcium, magnesium or aluminium, then a white precipitate will be formed. Because all of these are white, you'd need to do further tests to find out whether it's actually calcium, magnesium or aluminium you've got. Now, to determine if you've got aluminium or not, you can add sodium hydroxide in excess to the solution. And with aluminium, if you add excess sodium hydroxide, it turns colourless because the precipitate that you've just made dissolves back in the solution. So that will help you identify the aluminium. For the other two, you may need to do a flame test, and if it comes up as orange-red, you know then you've got your calcium. To remember the difference then between these white precipitates, if you remember that calcium and magnesium are in group 2, and the aluminium being in group 3 is the one that does something different. Okay, so the group 3 one is the one that will disappear when you add excess sodium hydroxide. Now let's look at the test for anions, which are the negative ions. First of all, we'll look at testing for carbonates. So that's if the second part of your compound was CO3. So for this test, you would place a spatula of your unknown compound in a test tube and add dilute acid. So we'd have our unknown compound in the bottom and acid added on top. We then add a bung and delivery tube and connect to a test tube containing lime water. If carbonate ions are present, then carbon dioxide will be released and the lime water will turn cloudy like shown in the image there. If you had a negative result for the carbonates, you might want to then test to see if your compound contained a halide ion. And the three that you need to be aware of for your exam are chloride, bromide and iodide. So if you remember, halide ions are from group 7 of the periodic table where you find the halogens. So to test for these halides, you would add a few drops of dilute nitric acid and a few drops of silver nitrate. So for the chloride ions, first of all, I'll show you the ionic equation. The silver ions from the silver nitrate react with the chloride ions, if they're present, to form silver chloride. And if chloride ions are present, the silver chloride is a white precipitate. For the bromide ions, again, the silver ions would react with the bromide ions to make silver bromide, but this time that is a cream precipitate. And if iodide ions were present, that would form a yellow precipitate. Now, to help you remember, if you think about the periodic table, you can think of the precipitate getting darker as you go down the periodic table. So white precipitate for chloride ions, cream for bromide, and yellow for iodide. So if you've got negative results for carbonates and halides, you might want to finally test to see if you have sulfate ions in your compound. So to test for sulfates, you would have your unknown compound in a test tube, and you'd add some hydrochloric acid and some barium chloride. And if sulfate ions are present, a white precipitate will form, and this is because barium sulfate is being formed. So the barium ions from the barium chloride react with the sulfate ions, if they are present, to form barium sulfate.
Okay, moving on to some content then for chemistry paper 2, topics 6 to 10. A little bit more on rate of reactions first. Just looking at these graphs like we did before, you might have massive product over time. The time might not be in seconds, you might have it in minutes or hours, depending on how quickly the reaction takes. And you might need to identify which is the fastest rate. So we said before, the area on the graph with the steepest gradient is the fastest rate of reaction. So if you're describing it, let's look at line A here. This is the fastest rate of reaction at section 1. Then the rate of reaction slows down as the gradient gets shallower, and then it's a much slower rate of reaction, and then it stops again. So you could describe how the rate of reaction changes, or you might be asked to select the fastest rate of reaction out of 3 lines. In this case, that would be A. We said we come back to the catalyst. We said before that it provides an alternative pathway with a lower activation energy. That's the GCSE bit. You won't get all the marks if you just say that it speeds up a reaction. Remembering reaction profiles from paper 1, they may well creep into paper 2 as well, because you might need to show on there how a catalyst is providing an alternative pathway. If you remember before, the activation energy is this line here from the bottom of the reactants to the peak. So if we're drawing a line with a lower activation energy, you would draw a line on like so, lower than the previous line. So whether it's endo or exo, you do exactly the same thing. Reversible reactions are reactions whereby the reactants make products and then the products can react again to make the reactants. The symbol for reversible reaction is here, and you will have to be able to draw that in the exam. And one example that they talk about is in the specification is hydrated copper sulfate. That's got water in it. So think to yourself, the one that's hydrated with water is blue. And then that will break down into anhydrous copper sulfate. That's a posh word of just saying the water's gone. Okay, anhydrous copper sulfate, which is white, and water is released. So this reaction here, if you've just got one substance which you heat up and break down to form 2, the forward reaction here is called a thermal decomposition reaction. And if you ever see this kind of reaction, it means it's not reacting anything. It means you need to take in heat to break it down. So this one is endothermic, going in this direction, because it's taking in heat in a thermal decomposition reaction. And in a reversible reaction, if one direction is endothermic, the reverse has to be exothermic. Looking at organic chemistry then, let's start off with this general formula. This says CnH2n plus 2. This is the general formula for an alkane. What the N means, you probably use this in maths, it just means for any number of carbons, you will have double that plus 2 hydrogens. So for example, if we had 2 carbons, C2, we would have 2 times 2 plus 2, which would be 6 hydrogens, and that would be one formula of an alkane. Let's look at the ones you need to know then. You need to know methane, that's CH4, ethane, propane, and butane. So monkeys eat peanut butter is one way to remember the order. Methane has 1 carbon, ethane is C2H6, and that has 2 carbons. Propane has 3 carbons, so that's C3H8. And butane, if you were asked to draw one, think to yourself, monkeys eat peanut butter, so that has 4 carbons. Start in the middle there. And every single bond is a single covalent bond in these molecules. And they are full up of hydrogen ions. And this has got hydrogen atoms, hydrogen atoms. And this has a special word. If it all has single bonds and is full up of hydrogen, this means these are saturated molecules. Think to yourself, S saturated, S all single bonds. Let's finish this one off then. Butane, if you're asked to write the formula for it, C4H10. Now these formulas here are called the displayed formula. So if they start talking about displayed formula in the exam, that's just the one that shows all the bonds in between them. So these are called hydrocarbons because they are just made up of carbon and hydrogen and nothing else. And we can burn these in a combustion reaction. Let's take methane, for example. When we burn methane, we're reacting it with oxygen in the air, and the products are always carbon dioxide and water. And obviously this can link to global warming. So ethane and oxygen would still make carbon dioxide and water, and propane and oxygen would still make carbon dioxide and water. If there wasn't enough oxygen in our reaction, we would do something called incomplete combustion, which is not very good. It produces a really smoky flame. And let's say methane and oxygen, we'd still produce carbon dioxide and water as before, but with incomplete combustion, we'd also produce carbon, which is soot, so solid black carbon, and carbon monoxide, CO, carbon monoxide, and that's bad as well. So the soot we'll talk about later causes global dimming, and the carbon monoxide is toxic and can kill you. Okay, so that's the alkanes. Fractional distillation then, this is where we are separating different substances by their boiling point. So when we dig down for crude oil, that has taken millions of years to make, it will be a mixture of hydrocarbons. You'll have some short ones, some very long hydrocarbons, and it will be a complete mixture, and it's not useful whilst it's a mixture. So the point of fractional distillation is to separate these. You heat the crude oil with a fossil fuel probably, so coal or something used to heat the fossil fuels. And then you are going to separate them by their boiling points. So the shortest ones have the lowest boiling points and they go to the top. Then you get your longer ones until you get right to the bottom where you've got very long chains. The ones at the bottom have a really high boiling point. So they come out of the bottom of the chamber because they're still next to the heat, they're still heating up, but they're not quite at that stage where they've boiled and risen up the tank. So you don't need to know the names of the products that come out of here or the order, but they're things such as petrol and diesel and gases. So gases come out the top, then you've got things like petrol and diesel. Petrol is slightly higher than diesel, and we'll talk about this in a minute, because if you needed petrol but only had lots of diesel available, you could crack that diesel, because it's a longer chain, and produce petrol to meet the demand of the population wanting petrol. So what can these be used as? Well, they're really useful fuels. The ones at the top that come out are really flammable, so they catch fire easily. They're very volatile, trying to say both things at the same time, which means they easily turn into a gas. So those are the ones at the top, low boiling points, flammable and volatile. The ones at the bottom have high boiling points, they're the long chains, and they are described as being very viscous. That means they are thick and gloopy and don't flow easily, whereas the ones at the top flow easily. They can be further processed to produce things such as solvents, lubricants, and polymers, which we'll come on to later. But in their raw source, they're best used as fuels. So we said before, if you wanted to produce a shorter chain like petrol from a longer chain like diesel, you could go through the process of cracking. Cracking takes place using a heat, I'll just get rid of that writing, using heat and a catalyst to break up a larger molecule. Now, it could break absolutely anywhere. It could break here and make two molecules, or it could break here and make two molecules. It doesn't matter where on the chain it actually breaks. So let's say we started with a long molecule like C8H18. When you crack it, you produce another alkane with single bonds and something called an alkene that has a double carbon-carbon bond. So the alkane, let's say for instance, you could put any products here in the exam. Let's say the alkane that we produced had 5 hydrocarbons, so it would be C5H. We need to double that up and add 2, so 12. So we use 5 of these, leaving 3, and we've used 12 of these, leaving 6. The product that you make will be an alkene. So that would be C3, because we've got 3 left, H6. And this time you can see that it's just double the number of carbon, not double plus 2. So this is what cracking makes, alkanes and alkenes. And alkenes have a double bond. So this one would have 1 double bond between 2 of the carbons, and then the rest of them are single bonds. Like so. For foundation, you won't be asked to draw these alkenes. You'll just need to know that cracking produces an alkane and an alkene. So C3H6. So you could have cracked that another way. Okay, you could have 3 carbons here and 5 over here. It doesn't matter what the products are, as long as they all add up to C8H18. The test for alkenes we need to know about is bromine water. And that goes from orange to colourless in the presence of alkenes. In alkanes, it will just stay orange. So you'll know where your alkene is because it will go colourless. So there's 2 types of cracking. One of those is steam cracking. So for this process, you would vaporize your hydrocarbons, so turning them into a gaseous vapor, and mix them with steam and heat them up, and that will then crack your hydrocarbon. Or you may well see something called catalytic cracking. It's got the word nearly catalyst in here. And this is where you vaporize the hydrocarbons again, but this time pass them over an aluminium oxide catalyst, and it will do the same process of cracking the molecule. So, chemical analysis. You need to know the test for some different gases. Hydrogen is one. If you put a lit splint in the sample and hear a squeaky pop, that means you've got hydrogen present. For oxygen, if you place a glowing splint in a sample, so you've lit it up and then blown it out so it's glowing slightly, it will relight if oxygen is present. Carbon dioxide, we should hopefully know this one. You bubble it through lime water, and if carbon dioxide is present, the lime water will turn cloudy. And again, like previously, because a precipitate has formed, a solid precipitate has made it go cloudy. The final one, chlorine, got to get this correct, bleaches damp litmus paper. Okay, so that's the test for chlorine. You might have touched upon that when you did electrolysis in paper 1. Let's talk about different compounds then. Some compounds are pure. Okay, so some materials are pure. They only contain either one element or one compound, nothing else. Others are specific formulations. Now, this is the definition you'll need to know. It's a useful mixture made from a recipe or a formula, you could write, for a specific purpose. So, for example, paint is an example of a formulation. In paint, you've got the pigment in there, you've got the resin in there, the binder in there, and they are all in specific amounts to make that particular useful purpose. Pure substances you will recognise because they have very specific melting points and boiling points. For example, you'll know if a substance is pure copper because it will have an exact melting point of 1083 degrees. It will have an exact boiling point of 2567 degrees. You find these data tables online, and they tell you the exact melting and boiling point of a pure substance. If you had a mixture or something that was impure, or a formulation, for example, you would not have an exact melting point for copper. So let's say you had a particular sample and the exam tells you that the melting point for copper was 1080 degrees. Even though that looks very close, that is not accurate, is not close to the true value. So this would be an impure sample of copper. It would contain some impurities, perhaps a little bit of sulfur or something like that. So only if they are exactly what the table matches can we class them as pure. Accuracy, if that comes up, in terms of these constant values here, they are accurate if your value is exactly the true value. So, chemistry of the atmosphere then. Scientists believe that the Earth began around 4.6 billion years ago. At that time, there was lots of volcanic activity, releasing gases such as nitrogen, carbon dioxide, ammonia, which is NH3, carbon dioxide, methane into the atmosphere. And the early atmosphere was very much like that of Mars and Venus today. So we went from an atmosphere that had lots of carbon dioxide in it to an atmosphere that now contains, comparably to everything else, very little carbon dioxide, loads of nitrogen and some oxygen as well. So how did it do that? Well, some water vapour was released from the volcanoes as well. That water vapour condensed to form the oceans. As the Earth started to cool down, the water vapour that was in the air condensed to form the oceans. And when that happened, a lot of the carbon dioxide from the early atmosphere dissolved into the oceans. And there it made the shells of early marine organisms. So it made the shells of, we call them calcium carbonate shells, of lots of different marine organisms. It also whilst it was being dissolved in the ocean, over millions of years, it would have also been crushed down into fossil fuels. So these calcium carbonate animals that died would have been crushed down and locked up in fossil fuels. As well as that, because this rock type occurs at the bottom of the seabed, they would have also been locked up in sedimentary rocks. So you had a situation where you've got lots of carbon dioxide in the early atmosphere, but as it's getting dissolved in the oceans, it is getting locked up in fossil fuels, sedimentary rocks, and in the production of calcium carbonate shells. As well as that, before the animals came along, really, we had algae around 2.7 billion years ago. 2.7, sorry, my writing, billion years ago. We had algae forming and plants a little bit later on. And they took in the carbon dioxide in a process called photosynthesis, which you should be aware of. And in the process of photosynthesis, they took in the carbon dioxide and they released oxygen. So the levels of oxygen in the atmosphere started to rise, which sustained other life. Until we got the composition of the atmosphere as it is today, okay, which is 80% nitrogen, approximately, that's rounded up. 20% oxygen, again, that's rounded because together they make 100%, but obviously we've got a few other gases. We've got carbon dioxide, 0.04%, and other gases like argon, water vapour, and things at less than 1%. So it's weird, but in the exam they will round these figures up and down normally, so it might not add up to 100% altogether. So an atmosphere of mostly carbon dioxide, dissolved in the oceans, made sedimentary rocks, fossil fuels, dissolved, made the carbonate shells of animals, and then taken in by photosynthesis, oxygen released, and we end up with the atmosphere like it is today. So chemistry of the atmosphere continued then. We're going to look at global warming. We touched on this in biology, so hopefully you'll remember my way to remember it, which is the soot sun produces the soot shortwave radiation, and that can go through the greenhouse gases, which provide a blanket around the Earth. So these are things like carbon dioxide, the first one, methane, and the lesser known one is water vapour. So always write carbon dioxide first and then methane and water vapour. So the shortwave radiation goes in, but all of the objects on the Earth absorb that radiation and reflect it back into the atmosphere. But this time, as it goes out, it is now long wave radiation. And that doesn't just go straight through the greenhouse gases. Some of it does, but some of it is absorbed and re-radiated back to Earth. So that is what is causing the global warming. The shortwave radiation goes in, it's reflected off of the Earth as long wave radiation, and the greenhouse gases absorb and re-radiate that back to Earth, causing a warming effect. Now we need that to some effect to sustain appropriate temperatures for life on Earth. But however, carbon dioxide levels are going up as well as other greenhouse gases, and that means more long wave radiation is being re-radiated, causing a warming effect. This is causing many consequences, including increased flooding, sea levels rising, changes in species distribution. So some animals are becoming extinct in different areas of the world because they can't adapt to the changing conditions, or they might move places. Okay, so this is meaning they're perhaps migrating away and moving to different areas. Increased frequency of extreme weather, so hurricanes and tornadoes and things like that. So there's a few of the consequences. And it's important that we all consider our carbon footprint, because it's the carbon dioxide levels that are going up. Our carbon footprint is the amount of carbon dioxide and other greenhouse gases released over the full life cycle of a product. So this could be anything from a company making a mobile phone. You could be talking about your own carbon footprint in your day-to-day life. You could be talking about the carbon footprint of a festival, a music festival, for example, and it's the total CO2 that's released. So it's in things such as transport to and from a place. It's in things such as fossil fuels and burning fossil fuels to generate electricity for certain things, etc., etc., and how those can be cancelled down. For example, many people are reducing eating meat, okay? And at the same time, they might be eating perhaps vegetables or fruits that come from far away in the world. So if you're eating perhaps avocados from somewhere exotic, they might be traveling on a plane and releasing lots of fossil fuels. So food itself will have its own carbon footprint. So that's something important to consider as well. Let's look at the main pollutants then. These are the links, and you'll see tables like this in the exam. Carbon dioxide, I want you to always link to global warming, as well as the other greenhouse gases. Solid particulates, for example, we talked about soot or carbon being produced in incomplete combustion, cause global dimming. They sit as a layer in the atmosphere and reduce the amount of sunlight going through. Sulfur dioxide. Now, this is such a common thing in paper 2 to talk about sulfur. Might link into the purity of fuels. If you see anything to do with sulfur being an impurity, which is making something not pure, in a fuel, for example, if you're trying to burn methane, but you realise your sample has got sulfur in it, well, that is going to react with the oxygen to make sulfur dioxide. So whenever you see sulfur, link to acid rain. And in fact, as well as sulfur dioxide, nitrogen oxides also cause acid rain. But these ones take place within a car engine. Okay, so very specifically, always put acid rain, but these take place within a car engine at very high temperatures. So we said before that 80% of the atmosphere is nitrogen. So if that goes in your car engine and reacts with oxygen, it can produce nitrogen oxides. It doesn't happen normally, like there's loads of nitrogen and oxygen in the air. They're not reacting normally, but they need really high temperatures. Both of these two can cause respiratory problems, so breathing problems as well. Carbon monoxide we came across earlier, CO, just one oxygen. That is toxic and it can kill people. Okay, it's called the silent killer because it's odorless, you can't smell it, and if your boiler at home is doing incomplete combustion because one of the pipes is blocked and it's not getting enough oxygen, you will be producing carbon monoxide, and that is toxic and can kill you. So we're going to look at using resources. So the first thing we're going to look at is a life cycle assessment. You can do this for any product that you are interested in. Again, something like a mobile phone, the company might be asked by the government or by the supplier to produce a life cycle assessment for that. So first of all, there's 4 factors. Raw materials. So these are things like, what are you using to make the phone? So it's all of the process involved in, for example, making the plastic. So for this one, you might be extracting crude oil, and you need to think about what effect that has on the environment. You might be using machinery to do that, which is burning fossil fuels and releasing carbon dioxide as you're doing that. You may well have to cut down trees to get to an area to mine it, for example, for the gold, for the connections that you're going to use within the electrical circuit of the phone. So there's loads of things that you can think about that will affect the environment when you're looking at the raw materials for the phone. The manufacturing and the packaging. So in all of these processes, they often involve some sort of factory which you need to power by burning fossil fuels to generate electricity. Again, that's going to be releasing carbon dioxide. It could also, if it's got sulfur impurities, be releasing sulfur dioxide, causing acid rain. And where's the packaging coming from? Where are you sourcing that from? That could link into deforestation again. Are you cutting down trees to generate your packaging? The use of the product. So can it be, is it just used once, for example, and then someone throws it away? Is it something that's used for a long time? When they're using it, are they needing to charge it up using electricity, again, burning fossil fuels and all of these things? So this is thinking about when the product is being used by the consumer. And finally, at the end of the life cycle of the product, how are you going to get rid of it? Is it going to fill up landfill? Has it got toxic chemicals in it which need to be disposed of carefully? Or can you recycle it? So all of this process is showing the effect on the environment of that single product. Sustainable development is linking into the resources and the resources that we're using, because it is the development that meets the needs of the present society without damaging future generations. You can imagine a tick box type thing in the foundation for this. So basically it means making sure that we're not digging up and mining the whole planet, chopping down all the trees and ruining it for future generations. We need to be sustainable. We need to make sure that we're using renewable resources where we can and not just exhausting all of our finite resources. Which brings us on to those two words. In chemistry, they use the word finite to describe non-renewable resources like fossil fuels. And in terms of making products and things, renewable resources would be our things such as wood and timber that we can replace. So if we're looking for sustainable development, we're going to want to reduce the finite resources that we're using and try and increase the renewable resources. And we want to try and do recycling as much as we can, because recycling means that less energy is used because we're not having to mine and dig for new materials. We're conserving the raw materials that we've got, which makes it more sustainable. And we're sending less waste to landfill. So recycling is really good for those three things. You need to know specifically about how glass is recycled. So you've probably been to the glass bins before, so you'll know the first point straight away, in that you separate the glass by the different colours of the bottles. So for glass recycling, the first step is to separate the glass by the colour. So you put green, brown and colourless glass in different bins. It's then crushed and melted, and then it's reshaped into new products. Okay, so that's a specific example you need to know about glass. Drinking water then, final couple of things in relation to water. Potable water is water that is safe to drink. Okay, so if you see the word potable, that means it's safe to drink. What that means is it has low levels of salt, and microbes. So you might have a little bit of salt in there, a little bit of microbes or bacteria, but they are low enough levels that they are not going to cause any harm. It is not the same as pure water. Pure water would be just H2O, nothing else dissolved in it or anything tainting it. It's just H2O. So pure water, again linking back to the boiling points, would have a boiling point of 100 degrees. Potable water might not have a boiling point of 100 degrees because it might have a few other bits in it that increase the boiling point. Water sources. So surface water is one. In the UK, we have lots of surface water. We have lots of lakes, rivers and reservoirs to collect our fresh water, which is our rainwater in. We could also get water from groundwater, so underground rocks where water is stored. And to get it, to make sure it is potable, we have to go through a process of filtration. So a large wire mesh, which will get rid of large objects like twigs and, I don't know, trolleys, plastic bags, bottles, whatever else has been chucked in the river. Then we have to filter out the smaller solid bits. So we put that through a gravel and sand bed. So the water is filtered through there and other solid bits like smaller twigs and leaves and things will be removed. And then finally, we need to sterilise it to kill microbes. And there are several ways we could do that. We could use ultraviolet light that has enough energy to kill the bacteria. We could bubble it through with chlorine or bubble it through with ozone gas as well. So either of those methods or all of them we might use to sterilise the water. Then it's potable and safe to drink, and we can put it through our taps. Now, in hotter countries, places like Saudi Arabia, for example, Dubai, where there's not a lot of rainfall, there are different steps you can take if there is not a lot of fresh water. And one of those steps is reverse osmosis. So normally osmosis would mean that the water would move from where there's a dilute solution, so a high concentration of water, to a low concentration of water. So normally, I'll just put normally there, that's the way the water would move. But with reverse osmosis, what they've done is they've taken salt water, which is over this side, which is from the sea, because they've got lots of sea water available. So they've taken their salty seawater and they've applied a great deal of pressure behind it, pushing it through a membrane, and that squeezes the water in the reverse direction of osmosis. Okay, in this direction. That's why they call it reverse osmosis. It goes against the gradient. Okay, so we require a lot of pressure for that. The other thing that they can do is distillation. Like we talked about before, they can take their salt water, heat it up, and make pure water. But in this case, it requires a lot of energy because you're burning fossil fuels to heat up the salty water. And it's therefore very expensive. So a lot of these hotter countries find it more difficult to get their drinking water, their potable water. Treating wastewater then. We produce a lot of waste, a lot of sewage water and things that we need to recycle because water is precious and we don't want to waste it. So we get a lot of waste from farmers and also from sewage systems, which we need to clear. So we first do a screening process, which is like a filtering process, really, to start off with, whereby we remove large objects from the wastewater. It then goes through a sedimentation process, and in this process, our wastewater separates into a sludge at the bottom, which is really thick. And then you get a fluffy layer on the top, which is called effluent. And you might have seen pictures about that, where this bit's really frothy and foamy and really light. So it just separates the products like so. Then there's two different processes. For the sludge, we do anaerobic digestion to break down all that waste material in the water. And for the effluent, we do aerobic digestion. So you might remember that the effluent is closer to the air because it's at the top. So that might be a good link to think that's the one that has aerobic digestion. So for the effluent, air is pumped into it, and then bacteria break down the effluent in aerobic conditions. For anaerobic digestion, and finally the water is released back into the rivers. So the bacteria break down any waste product and then the water is released back into the rivers. For anaerobic digestion, if you are a separate scientist, you would have looked at this before in biogas generators. So this is where the link is between biogas generators for separate scientists. So bacteria break down the sludge, but this time in anaerobic conditions. And the two products are methane, which is a biogas, which can be used as a fuel, and fertiliser, which can be used by farmers to put nutrients back into the soil. So as you can see, there's not a lot of higher tier content on there. There's just three things to have a look at. We've already looked at this one, calculating rate using a gradient. So I'm not going to look at that again, but that's where we had our rate graph and we drew a tangent to measure the rate at a particular time point. That is a higher tier only thing, so I expect that in the exam. Equilibrium and the Chatelier's principle, and phytomining and bioleaching. So let's go through those now. So first of all, equilibrium and the Chatelier's principle. Let's look at this example here. You've got an example where you've got two gases reacting. So you can think about what things can affect the rate of reaction in gases. We've got nitrogen reacting with hydrogen in a reversible reaction to produce ammonia. And for separate scientists, this is also the equation for the Haber process. So Le Chatelier's principle says that when conditions of a reversible reaction change at equilibrium, the system will respond to counteract that change. And there's several changes that could happen. You could increase the pressure if you're talking about a gaseous system, you could increase the temperature, or you could increase the concentration. So just look carefully at the system that you've got. If this wasn't involving gases, you wouldn't be talking about increasing the pressure. Let's look at concentration first of all. Imagine if you're looking at acids or something like that reacting in a reversible reaction. If you increase the concentration of reactants, so everything on this side of the equation, the system will respond by making more products. Because you've increased the concentration of reactants, the system wants to decrease the reactants again. And in doing so, it makes more products. So the reactants react together and make more products. So if you increase the concentration of these, more ammonia would be used, for example. The equilibrium would shift to the right, so you produce more ammonia, and that would counteract that change because then the concentration of the reactants would go down again. If you're looking at temperature, this will depend on which way is endothermic and which way is exothermic. Normally in the exam, they will help you out by telling you in the question. If not, you might need to look out for it. And the way to look out for it is if there's one product this side, that will be broken down in a thermal decomposition reaction. For that one, you need to take in energy, so that's endothermic in that direction, and in the opposite direction, it's exo. But if in the exam they had two products here, they would give you a hint as to which one was exo and which one was endo. So for temperature, if you increase the temperature, it will favour the endothermic reaction because this is a thermal decomposition reaction, which means that heat is taken in to break down this ammonia. So in the example above, the equilibrium will shift to the left, which means that more of the nitrogen and hydrogen will be produced because the endothermic reaction is in this direction. If you do the opposite and decrease the temperature, that favours the exothermic reaction. A little bit more difficult conceptually to understand, but if you understand that increasing the temperature will favour the endothermic reaction, then think to yourself the opposite will favour the exothermic. So decreasing the temperature will favour the exothermic reaction, shifting the equilibrium to the right, so more ammonia would be produced. For pressure, if I clear the screen, that's all to do with the number of moles in the equation. If we remember, this equation says that 1 mole of nitrogen is reacting with 3 moles of hydrogen to produce 2 moles of ammonia. So we could kind of represent it like that. If you increase the pressure, it will favour the reaction with the most moles. So if you think about collision theory, that kind of makes sense because if you're squashing these closer together, you're going to get more collisions between these molecules. So in the example above, the equilibrium will shift to the right because it will favour an increase in pressure will favour this reaction because it has 4 moles altogether compared to 2. So the equilibrium will shift to the right and you will produce more ammonia. If you decrease the pressure, the opposite will happen. The equilibrium will shift to the left and you will produce more nitrogen and hydrogen. So, phytomining, something completely different now. Phytomining, P for phytomining, is to do with plants. Now, for higher tier, you need to be aware of the problem that many of our finite resources of copper are running out. So ores are rocks that contain metals, and many of our high-grade ores that contain copper, which contain lots of copper, are running out. So now we need to use new technologies which will get copper out of low-grade ores, which are rocks that contain a little bit of copper, but it's not very economical to extract. It would cost a lot of money to dig this up with mechanical equipment, and it would make the copper very expensive, and not many people would want to buy it. So instead, they need to find new technology to try and get the copper out of these low-grade ores. So this one is to do with plants. First of all, you'd have your ore, and you'd grow plants on your low-grade ores. The plants would take up the copper in the leaves, and it will build up in the plant. You will then burn the plants and harvest them, so set fire to them, or cut them, harvest them, dry them out, and then burn them. And then you would end up with some ash which contained copper. Now, unfortunately, copper is not magnetic, so you can't just put a giant magnet here to extract the copper. You can't do that. You'd have the plant material and the copper. So you might link back to paper 1 here, because what you could do is you could extract by electrolysis. So let's imagine you added some sulfuric acid to make copper sulfate. You could then do electrolysis of copper sulfate to extract the copper. Or again, you could add the sulfuric acid to make copper sulfate, and a really cheap method is to do a displacement reaction with scrap iron. So if you added iron to the copper sulfate, you would end up with copper plus iron sulfate. Okay, so that one's phytomining, growing the plants. The plants are taking up the copper from the ore, then you harvest them, dry them, burn them, and then you have to think about either electrolysis or displacement to extract it. For bioleaching, it's very similar, but this time you are using bacteria. So B for bacteria, B for bioleaching. Bacteria is grown on a low-grade ore. It's very cheap, so you can grow lots of it and it will divide rapidly. So this is quite an advantageous process for that respect. And the bacteria produces a leachate, which is a liquid solution containing the soluble copper compounds. So they do all the work for you. And then again, you can extract it by electrolysis or displacement. So you don't need to know this process in a lot of detail. You just need to know it involves bacteria and they produce a leachate containing the copper compounds. We're going to move on now to separate science only. So there's quite a bit more on alkenes for separate science, and then moving on to carboxylic acids, esters, alcohols, polymers, a little bit about metals and properties, corrosion, Haber process, NPK fertilisers, and we're going to start with this, the required practical and identifying ions, which then links into flame emission spectroscopy as well. So identifying ions is the required practical. This is the bit that nobody finds easy. There is a lot of different practicals to remember for this. So why do we do it? Well, let's have a look at this compound here. This could be absolutely anything. You could be asked in an exam to describe the test that you would carry out to identify the ionic compound. So an ionic compound is consisted of a metal and a non-metal. So for example, it could be calcium sulfate, it could be sodium chloride, it could be magnesium carbonate, magnesium bromide, potassium iodide, or copper sulfate. Okay, it could be any one of these things if we didn't know what it looked like. So we need to do some tests. The first test we do would be to work out the positive ion, okay, the metal ion, and that would let us know what the first bit is. And then we work out what the negative ion was, and we could put those together to identify the compounds. That's why we do it. Let's start off by testing for the positive ions, which we call the cations, because they're linked into the fact that they would go to the cathode. So the cations, flame tests first of all. You have a wire loop of unreactive metal, okay, it can't react with the metal that you're going to put on it, otherwise it will make a different colour. For example, platinum. You clean it by dipping it in acid. That will react with any of the metal, getting rid of it, and then putting it in a blue flame until it burns without any colour. You then allow it to cool and dip it in your sample. Here are the results. If you have calcium, you will have an orange-red flame. If you have sodium, you have a yellow flame. If you have lithium, that's a crimson flame. Potassium is a lilac flame, and copper is a green flame. In the exam, they really like the idea of masking. If you find it difficult to identify the metal ion from the flame test, it could do with masking, which is where you have two different metals in your sample and there's two different colours showing and one of them is hidden. For example, if you put calcium and sodium together, if they were in the same sample, you might just see the orange-red flame because the yellow one might be masked by that stronger colour. Okay, so look out for the idea of masking in the exam. If we didn't do a flame test, there are other tests that we can do for testing for metal ions. So this is the first one, adding sodium hydroxide to your unknown compound. So you'd put some compound in there, add your sodium hydroxide, and a precipitate will form. Okay, a precipitate will be a solid because it's insoluble, and it'll be an insoluble hydroxide. The colour can help you identify the cation. So a copper precipitate would result in a blue colour. An iron 2 from the transition metals, remember they can make ions with different charges, so this will be an Fe2+, that's why we call it iron 2, would make green, and iron 3 would make brown, so Fe3+. Remembering transition metals are the ones that form colour compounds, so that might help you remember these are the ones that have coloured compounds. You'll recognise copper being blue from things like copper sulfate, so it's just a case of remembering iron 2 for green and iron 3 for brown. Now there's three that all make white precipitates, and they are calcium, magnesium and aluminium, so that's not particularly useful. And if you had a white precipitate, you'd have to do further tests to identify which one it is. Now with aluminium, this one is the odd one out of these two because calcium and magnesium are both in group 2. So this one's the odd one out because that's in group 3. So think about that one being the odd one out. And this is the one where if you add excess sodium hydroxide, it turns colourless. So if you got a white precipitate and you added more sodium hydroxide, the precipitate redissolves and it will turn colourless. So you know you've got aluminium. For the other two, you might have to do a flame test and see if it comes out as orange-red for calcium or not. Testing for anions then, the negative part. For carbonates, you place a spatula of the unknown compound in a test tube and add dilute acid. You'll connect that with a delivery tube, a bung and delivery tube, to a test tube with lime water. And if that goes cloudy, then carbon dioxide will turn the lime water. Sorry, if it turns cloudy, the carbon dioxide is present. So, for example, if previously you have identified sodium as the metal ion, if this test became positive, you'd know your substance was sodium carbonate. If this didn't go cloudy, you would have a think again about what this could be and do another test. For example, you could test to see if it was a halide ion. It could be perhaps sodium chloride or sodium bromide or sodium iodide. So you would add a few drops of dilute nitric acid, okay, HNO3, and a few drops of silver nitrate, AgNO3. This might remind you which acid to use, because silver nitrate and nitric acid, nite. What will happen in this reaction is you will form a precipitate because the silver ions will react, if present, with the halide ions to make a precipitate. So, for example, if chloride ions were present, you would make silver chloride, that is white. If bromide ions were present, you'd make silver bromide, which is cream. And if iodide ions were present, you'd make silver iodide, which is yellow. To help you remember that, it goes darker as you go down the periodic table. So a nice visual there to help you. You start off with white and then cream and then yellow. It goes darker as you go down the table. So let's say that you ended up with a white precipitate. That would mean you'd have sodium chloride if we'd identified our previous ion as sodium, for example. Or you could have sodium bromide, or you could have sodium iodide. If none of those tests were positive, you might want to test again and see if your negative ion was a sulfate. And to test for sulfates, our final test, you add a few drops of dilute hydrochloric acid and a few drops of barium chloride solution. And again, you're going to make a precipitate. So if you add those together and you end up with a white precipitate, that is the result of barium sulfate being made. So if you've got a sulfate present, that will react with the barium and the barium chloride to make barium sulfate. And that means your negative ion is a sulfate. So you would have made sodium, you would have identified it, as sodium sulfate, for example, if previously you identified your metal ion as sodium. And that's just showing it there. Barium ions and sulfate ions making barium sulfate. Solid there, look out for that. That's showing you that a precipitate is formed if it's got a solid. So, I said before that these testing for ions can link back to distillation. So, if you wanted to make sure before and after, make sure before that you had sodium chloride and after that you didn't, you might want to test the sample for sodium chloride. So, you'd test using a flame test, for example, and yellow would indicate the presence of sodium ions. And then for the chloride bit, you would test for chloride ions by adding a few drops of nitric acid, because it's a halide, silver nitrate, and a white precipitate would be a positive test for chloride ions. So they might link this in with the distillation practical, so look out for that one. Flame emission spectroscopy is an example of an instrumental method. Now, they might talk about masking in the terms of the flame tests and ask you to think about something you could do to improve the accuracy of your results. And flame emission spectroscopy is one of those things. So your sample is placed in a flame, and when it does that, their electrons become excited. So what they do is they will be able to move, this links into the physics topic, to a higher energy level. Okay, so they're moving to a higher energy level. However, they will then fall back to their original energy levels, and when they drop back to their original energy levels, they transfer energy as light. So as they're falling back, they're emitting radiation as light, and this comes up in physics too. When they do that, you will have these spectra created because different ions, so different metal ions, produce different wavelengths of light due to their charges and electron structures being different. So every metal atom is different. It will have a different arrangement of electrons, different number of shells, etc., number of electrons in the outer shell. So it will produce a unique spectrum like so. And that will help you identify a metal. So if this is our unknown metal, on the internet you will have reference spectrums. Okay, so these are fixed spectrums which will show you exactly what a particular metal will look like. And you would compare these to the diagram above and see where the lines match. If this is made of two metals, you may well have to look at two different spectrums and see where the lines are matching. Instrumental methods, that just means using machines. 3 marks. They are faster, more accurate, and more sensitive than non-instrumental methods. So if you're looking at flame emission spectroscopy, these are faster, more accurate, and more sensitive than doing flame tests alone. Okay, this part of the topic they call organic chemistry. Anything to do with carbon, they call organic chemistry. So here are our alkenes. And again, monkeys eat peanut butter will be important, but we don't have the M bit. We don't have methane. It doesn't exist because you can't make an alkene with one carbon, because alkenes very specifically have the functional group C double bond C. So here we got ethene. The functional group is C double bond C, like I said, propene and butene. The functional group is the one that is in the same, is in all of the alkenes. So it's repeated in all of the alkenes. And then the structure just differs slightly. So 2, 3, 4 carbons. The general formula is CnH2n. And pentene, for example, if you're asked to draw this, or any of the ones, then pentene would have 5 carbons. So only one of them has a double bond. It's easier just to draw it at the start, and then we draw the extra ones on. And then for each carbon, that has to have 4 bonds. So there's 2 there, so that can make 2 more. There's 1, 2, 3 around that one. So it doesn't matter if it goes top or bottom, but that will make 1 more. And each of these will have, again, 4 bonds each, like so. So you might have to draw those in the exam. You might remember that the test for them is bromine water, like we said before, which goes from orange to colourless if alkenes are present. Alkene reactions, we've got combustion, and most of the alkenes are more reactive than alkanes. However, when they do combustion, they tend to undergo incomplete combustion, which means they burn with a smoky flame, and they're producing the carbon and the carbon monoxide like we discussed before. There's several addition reactions that they can go through, so they can add hydrogen to them, add water, or perhaps add a halogen. And in all of the times, they basically are opening up that double bond. So if we had ethene here, in the reaction, they are opening up this double bond so that they can add things to the molecule. So for example, in addition of hydrogen, that's called hydrogenation. The double carbon-carbon bond opens up and hydrogen is added to make it a saturated molecule. Whilst it's got the double bond, it is unsaturated, and then we open up the double bond, adding the extra bonds, making it saturated again. For water, alkenes and steam make alcohols. Okay, so for example, propene and steam would make propanol, ethene and steam would make ethanol, etc. And finally, the halogens, again, you're opening up that double bond and you are adding a halogen to it. So in this case, this molecule has added 2 bromine atoms. So you've opened up the double bond, added 2 bromine atoms. Anything that's related to 2 in chemistry called di. So this molecule is called, this one would be called dibromoethene. But in this example, double carbon-carbon bond opens up and a halogen is added. So unrelated to this, because this is bromine, but chlorine and propene, for example, would make dichloropropane. Okay, so you're making it saturated again, so you're making it the propane, and you're adding 2 chlorines to that. In this example, if I just clear the writing for a minute, in this example, I started off with ethene that would have had a double bond. I've opened up that double bond, got rid of that, and added bromine, so it would be dibromoethane. Okay, so in this example, dibromoethane. So di meaning 2, there's the halogen bit in there, and then you've got the saturated molecule again. Remembering, as we said before, that bromine water turns from orange to colourless. So when you're adding bromine water, this is essentially what you're doing, changing it into a dibromo molecule. Addition polymerisation then. This is when we're adding smaller monomer units together to make a polymer. And if you're trying to squash loads of monomers together, you need pressure and a catalyst to do that. So again, you might be looking at displayed formulas like this. This is the monomer. You've started off with an alkene here with a double bond, and the N just says that you're going to have many of these. So if you're asked to draw a monomer, you draw the alkene in with a double bond inside brackets. And everything else tends to be bunched up here. So we just put the CH3 here, or it could be C2 with the H's down here, depending on the molecule. So if we put lots of those together under extreme pressure, we can produce a long molecule. So there's our monomer, and we want to join them up to make a long polymer. Because it's very long, we don't want to draw out the whole of the polymer. So we just draw a section of it. So if you're asked to draw a repeating polymer unit like this, you break the double bond and you extend the double bond through the brackets. That's it. Nothing else fancy, but you can see here the only difference is that I've broken up the double bond and extended it through the brackets to show that in fact this would be part of a long chain of loads of repeating units. Hence why we've got N there now, just to show that if you had 10 monomers, there'd be a 10 long chain of these repeating units. Moving on to alcohols and carboxylic acids then. Alcohols all are part of the same homologous series. So homo meaning the same, they're all part of the same group of molecules. So they're a group of compounds that react in a similar way. Just like the alkenes are part of a homologous series and alkanes are part of their own homologous series. They have a functional group. This is the group of atoms on the molecule that determines how they react. And for alcohols, the functional group is OH. So again, using our prefixes, this has one carbon, so this would be methanol. This would be ethanol, and this would be propanol. And if you're asked to draw one, let's say we're asked to draw butanol, these are the four we need to know, methanol, ethanol, propanol, and butanol. Start with the functional group. It could be like that, or you could have done it like that. Either way is fine. And then you add your carbons on. So butanol's got to have 4 carbons, like so, and then finish with the hydrogens all around it. So my advice is to start with the functional group and then work backwards and put all the hydrogens in. All single bonds in an alcohol. When they dissolve, they are soluble. When they dissolve, their solutions have a neutral pH. So there might be a question asking you to identify whether something is an alcohol or not with a table of information. If it's got a neutral pH, it's an alcohol. It's a useful solvent. So we can use it, for example, in chromatography, like we discussed right at the beginning, or of fuels like spirit burners you may well have used in the lab with ethanol and methanol in. You need to know that they react with sodium. Bit of a random equation that we need to know about. But let's say, for example, sodium reacting with ethanol would make sodium ethoxide. I very much doubt they'll ask you to recall that, but they do want you to know that it produces hydrogen as well. So sodium and ethanol would make sodium ethoxide and hydrogen. Again, if you reacted methanol with that, you'd make methoxide and hydrogen gas still. Now, to get from alcohols to carboxylic acids, you need an oxidizing agent which will add oxygen to our molecule. So this could either be by microbial action, so for example, microbes in the air can do this, or it could be a chemical that does this. Microbes in the air, because if you have ethanol in your wine and you leave your wine bottle open, the microbial action will add ethanol to that and turn your wine acidic because it will make a carboxylic acid. Or you can do this in industry by adding chemicals. These are carboxylic acids. They have the functional group COOH, okay, like so. So they're all part of a homologous series, so a similar group of atoms, a similar group of compounds, sorry. And this would be methanoic acid because it has 1 carbon, ethanoic acid, propanoic acid, and then if you were asked to draw, for example, butanoic, start with the functional group, start with that bit, and then work your way backwards. You've used 1 carbon, so you've got 3 more, and then add your hydrogens round. Okay, so you might be able to ask to draw either carboxylic acids or alcohols. So this would be, what I've just drawn would be butanoic acid. Carboxylic acids react just like any other acids with carbonates, but they make a different salt. If you remember, the general reaction is an acid plus a base makes a salt plus water plus carbon dioxide when they react with a carbonate. So, for example, if methanoic acid reacted with sodium carbonate, you would produce sodium methanoate, this is the name of the salt, plus water plus carbon dioxide. This will be exactly the same. If it was ethanoic acid, it would make ethanoate. If it was propanoic acid, it would make propanoate. And if it was butanoic acid, it would make butanoate. They are also, this came up in paper 1 and it might come back again, weak acids. Okay, carboxylic are weak acids, which mean they only partially ionize in water. So if you had the same concentration of carboxylic acid as a strong acid, the strong acid would have a much lower pH, and these carboxylic acids would have a much higher pH because they only partially ionize in water. That means there's fewer hydrogen ions floating about in the solution. To make esters, you react carboxylic acid with an alcohol, and that will produce an ester and water. So, for example, if you had ethanol, you could react that with ethanoic acid in the presence of a concentrated sulfuric acid, and that is used as a catalyst in the reaction, to produce an ester plus water. Now, this is the only ester that you will have to remember the name of, ethyl ethanoate, made from ethanol and ethanoic acid. You won't have to remember other ones apart from that. They may talk about them in the exam, but this is the only one that you would have to recall. So these are really volatile and fragrant compounds, these esters. And this is how we'd show it as an equation here. Ethanol plus ethanoic acid making our ester, ethyl ethanoate, and water. If you see the way the molecules are written here, you can see obviously their functional group. So this is the alcohol, and then the hydrocarbon bit is written before. Again, for ethanoic acid, they tend to write the functional group and then the hydrocarbon bit before. For an ester, this is the functional group, Cu. Okay, so for an ester, you'll see it in the middle here as opposed to the end of the molecule. And in the written formula here, you can see it just down there. Okay, moving on to metal alloys then. Something that you have to remember off by heart. You have to remember bronze is an alloy of copper and tin, and you might be asked for uses. So they're used as medals and ornaments. Brass is copper and zinc, which is used for things like water taps and door handles. You can have gold alloys, which might be a mixture of gold and perhaps cheaper metals to make the jewellery a little bit cheaper, and they're used in jewellery. And also gold is often quite soft, so the alloys, if you remember from paper 1, the alloys are different size metals which disrupt the layer, different size atoms, which disrupt the layers of the metals. So with an alloy, you get a lot harder substance because the layers can't slide easily. So a lot of these purposes for alloys is to make them harder. Aluminium alloys, so aeroplanes are made out of aluminium alloys because they are low density. You're going to want them nice and light to be able to fly in the air. But an alloy of aluminium, again, makes it harder than pure aluminium itself. An important alloy is steel. Steel is an alloy of a metal and a non-metal, so iron and carbon. Here's our different examples. Low carbon steel, and if you think about it, it's having just a small percentage of carbon in there, so maybe the layers are less disrupted. That is still easily shaped. So those will be used for like car bodies and things that you want to make into unusual shapes. If you add more carbon in there, so you've got a higher percentage of carbon, you make something that's much stronger and inflexible. So things like bridges are made out of high carbon steels. The final steel alloy that you need to remember is stainless steel, which is an alloy of iron, chromium, and nickel. And with that, and carbon in there as well. And with that, you have a metal that is resistant to corrosion and very, very hard. So cutlery is a good example of something that's made out of stainless steel, because when you put it in the dishwasher, you won't want it to react with anything. And when you're cutting food, you want it to be very hard. Ceramics are non-metal materials, and they are not organic compounds. So if you remember before, that was to do with carbon. So these ones aren't carbon-based compounds, but they are still non-metals. They have high melting points. And one example is clay. When you dig up clay, it's very soft and you can mould it and you can shape it when you mix it with water. If you then burn it and fire it, you make a very hard substance. So you can make bowls and other pots and plates and things out of clay. Glass is another one. There's two examples that you need to be aware of. It's a ceramic material. There's soda lime glass, which is made out of limestone, hence the lime bit. Sodium carbonate, which is the soda bit, and all glass is made out of sand. So limestone, sand, and sodium carbonate. And if you want something with a higher melting point, again, you could make borosilicate glass, which again is sand, which is the main constituent of glass, and something called boron trioxide, which is where the boro bit comes from. Composites are an everyday material that's really important. The basic structure of a composite is made out of fibres, so some sort of fibres which make it really strong, and that's called the reinforcement bit. And then to bind those fibres together, it's surrounded by a matrix, okay, which acts as a binder. So, for example, fiberglass is a composite whereby the glass bits are the fibres, so strong fibres of glass, and they have a polymer plastic matrix over the top to make it bind together. Carbon fibre is carbon fibres, or could be nanotubes. They could make an appearance again from paper 1. Nanotubes with a polymer matrix. Concrete is a mixture of aggregates, so small rocks and things like that, acting as our reinforcement, and our cement over the top will bind that all together to make our concrete. And wood has natural cellulose fibres and an organic polymer matrix that binds all of those together. Looking at polymers then. Polymers, we're talking about plastics. Okay, so we've got low density polymers. The conditions which the polymers are made in, we said before that when we're making polymers, we need pressure and a catalyst and a little bit of heat as well. And the temperature and pressure in the catalyst that we use will determine whether we make a low density polymer or a high density polymer. So a low density polymer would be made out of strands like this. We can push them together a little bit and they'll make things like plastic bags and bottles. So moderate temperature, high pressure, and a catalyst. A high density polymer, the polymer strands are much closer together and you can push them closer together. They make a really hard plastic polymer because you can squish all those together. You make those at a lower temperature and pressure, and you use a different catalyst. So the conditions for making the polymer are really important. They're useful for things such as water tanks and drain pipes. And much harder plastics are your high density ones, things like helmets and things like that. Two specific form of polymers that they want you to know about are thermosoftening polymers. You might have had a gum shield in the past that's a thermosoftening polymer because you can heat it up and remold it to the shape that you want. So these have quite a low melting point because you can use a kettle to heat them up and boil them in, and melt them in hot water. So they can melt and remold. So those polymers can kind of cross over each other and are just loosely over each other like that. For a thermosetting polymer, this has a much higher melting point, because it's got cross links between the chains. So if you see something like this, you will see cross links, which you might have to label between the polymer chains. This makes it much harder and it won't soften when it is heated. So corrosion in general is the destruction of materials through chemical reactions with substances in the environment. So it's often to do with metals reacting with substances in the environment. A particular one that you need to know about is rusting. And rusting is to do with the metal iron very specifically. Iron reacts with oxygen and water to make hydrated iron oxide, otherwise known as rust. Now, importantly, both oxygen and water are needed for this process. You might see some results from an experiment a little bit like this, and you might need to determine the conditions needed for rusting. Let's have a look at this one. A few key points. If you see boiled water, that means that the oxygen has been removed. Okay, so in this example, you've got a nail in water, so it's in water, but there's a layer of oil on the top which will stop any oxygen getting in, and it's been boiled. So it's in water and there's no oxygen. So because it requires both, that shouldn't rust. You've got another example here where the nail is in calcium chloride, so you might see like a white powder around the nail. That means this calcium chloride absorbs water. So in this case, you have no water because it's absorbed by the calcium chloride, but you do allow air in which contains the oxygen, so you do have oxygen. But because rusting needs both, this nail should not rust. And finally, you've got a situation where you've got air and water. You might have some of the nail out of it. If you have a look at the results, that bit might not be exposed to water, so that might be not rust. But where you've got the oxygen being able to dissolve in the water from above and the water itself, you will have rusting. So you might need to determine the results of that kind of experiment. To prevent rusting, you could paint the nail or put some oil or grease around it, and you might need to link back to what you're preventing from getting to the nail in terms of oxygen and water. You could electroplate it, so using electrolysis to coat the iron in a corrosion-resistant metal. So if you made your iron the negative electrode and you had a pure metal over here as your positive one in an electrolyte, the ions would move over to the negative electrode and coat it for you in a protective metal. Or you could use sacrificial protection. This means you sacrifice one piece of metal to protect the iron. You might see this on ships, for example. If ships are made out of steel, that's got iron in it. So you might see a big lump of zinc, for example, on the side. This is because the zinc is more reactive, so that will corrode first, and that is therefore protecting the iron which is in the steel hull. Galvanizing means spraying something in a zinc coating. So again, you could have a metal which, rather than doing electrolysis or electroplating, you could spray it in a zinc coating to galvanize it. The zinc is more reactive, so that will react first with oxygen and things like that, creating an oxide coating and therefore protect the metal underneath. But we wouldn't call it rust. We only call iron oxide rust. We don't call zinc oxide or aluminium oxide rust. Haber process then. We talked about the equation earlier. Nice zip through this one. We said that the Haber process was nitrogen reacting with hydrogen to produce ammonia. So in the top here, you have nitrogen from the air going in, and you have hydrogen, which is normally made from methane, natural gas, going in as well. You have an iron catalyst, which is to lower the activation energy of the reaction, speed it up. The nitrogen and the hydrogen will react inside this vessel and will produce ammonia, which is cooled and turned into a liquid. So the ammonia is cooled and turned into a liquid, and Every now and again, the tap is released and that is taken out when it's reached equilibrium. Then the nitrogen and the hydrogen are recycled back round in the chamber. So those are recycled, and it's the liquid ammonia that's taken out of the bottom. As well as the ion catalyst, the temperature is at 450 degrees C and the atmospheres are 200 atmospheres of pressure. However, this has a compromise, because with the Chatelier's principle, we said to favour the exothermic reaction and produce more ammonia, we'd want to lower the temperature. However, if we have a low temperature, lower than 450 degrees, this will also mean a low rate of reaction. So we could do this to produce a greater yield, however, it would take far too long. So this is a compromise in that they have a 450 degree temperature so that it makes not the optimum yield, but an okay yield, and the reaction happens faster. And the pressure is a compromise, because we said before, to favour this reaction, we want to increase the pressure to produce more ammonia. But increasing pressure in vessels like this is very expensive and very dangerous. So we can't increase it too high. So again, this is a compromise on what we can best do with the equipment that we have. NPK fertilisers are for separate science only. There's a little bit more content to go for you guys, not too much, so do hang in there. Fertilisers are used by farmers to return nutrients back into the soil. So you've got NPK fertilisers, and for this one you may well look at calculating ratios. That could be another maths thing that comes in, because these are a particular formulation containing specific ratios of nitrogen, phosphorus and potassium. To get the nitrogen salts, we can use the ammonia that we've just made in the Haber process, react it with nitric acid, and then we can make ammonium nitrate, and we can put a certain percentage of that in our fertiliser. So ammonia plus nitric acid making ammonium nitrate. So ammonium is NH4. For potassium salts, which is the K salts, we could mine, so dig up potassium chloride and potassium sulfate, which occur naturally. This one's where it gets a little bit more difficult, the phosphate salts. So phosphate rock can be mined, but it is insoluble, it doesn't dissolve. So this is one that you might want to come back to at the end of the video if you're struggling with this bit. So it's reacted with acids to make the salts for the fertiliser. So there's three reactions that you need to be aware of. You need to be aware of reacting phosphate rock with nitric acid. You can produce phosphoric acid with that and calcium nitrate. So you could use that nitrate as part of the nitrogen part of the fertiliser over there if you wanted to. But this is the useful thing which you'll use a little bit later on. If you react the phosphate rock with sulfuric acid, you produce a calcium sulfate and a calcium phosphate. Okay, and they call this one single superphosphate. And finally, using the phosphoric acid that you made up there, you could react the phosphoric rock with phosphoric acid and produce something that has just one product, which is calcium phosphate, which is your triple superphosphate. So it's the phosphates here that you'd use for the P part of the NPK fertiliser. So maybe worth pausing there and having a look, or coming back to look at those a little bit later on. So that is it. If you're doing foundation separate, I will leave you there because there are only a couple more bits to do which are for higher tier only. And as you can see, higher tier only, I suggest that you focus on these two bits. Condensation, polymerisation and polypeptides is what we're going to look at. So in addition polymerisation, all the monomers are the same. They have the just one functional group as well. So they have one functional group and they are all the same monomers. We're going to look at condensation polymerisation first. So again, it's making a polymer, breaking down the words, making a long chain, and the condensation bit, in this process, water is released. Okay, so breaking down the words, we're realising roughly what's going to happen. In example 1, we are going to use 2 different monomers with 2 or more functional groups. So addition polymerisation just had 1 functional group and was the same monomer. So that's the difference. So for example, previously we said that an alcohol and a carboxylic acid reacts to make an ester and water. Okay, but it's making the ester. In this case, add that bit on. In this case, we are looking at 2 different monomers, each with 2 or more functional groups. So di means 2. So essentially, a diol is an alcohol, but with 2 functional groups. So you're going to see 2 OHs on it, because it's a diol. A dicarboxylic acid, again, is a different monomer, okay, and it has got 2 functional groups for a carboxylic acid on it. They are going to react together. So this is one monomer reacting with a different monomer. I'll just do one as a circle, one as a square. And that is going to make a polymer like so. And because this time it's not just making an ester, it's making a polymer, we call that polyester. Okay, polymer ester, polyester. And the water bit is because it's a condensation polymerisation reaction. It doesn't have to be water in all of the cases that you'll see, but a small molecule given off. So a diol is represented a little bit like this. The box just covers up all the hydrocarbon stuff, all the carbons and hydrogens that aren't important. But if you see 2 alcohol groups, that's a diol. If you see 2 carboxylic acids, that's a dicarboxylic acid, and they react together, you can see the functional group for the ester there. They react together to make a polymer, which is polyester and water. The other option, example 2 for condensation polymerisation, this is where we make our polypeptides. So one type of monomer this time, in this case our amino acid, because it has 2 different functional groups. This one is the amine group, and this one is the carboxyl group. And we talked about the amine group in biology because we're talking about deamination and removing it. So we know it's got 2 different functional groups rather than this one. Alcohols only have OH, but a diol has 2 of those. These have 2 different functional groups. So if we want to add amino acids together, they form polymers called polypeptides, which is essentially a protein. Okay, because 1 or more long chains of polypeptide is called a protein. And if you link back to biology, you know that they can fold up to make specific proteins and specific hormones and enzymes and things like that. So amino acids are going to join together to make a polypeptide and water in our condensation polymerisation reaction. This is where the water comes from. You can see the hydrogen here, hydroxide here, reacting together to make water. Coming together to make water. So that's the second example of condensation polymerisation. And then other naturally occurring polymers that you need to be aware of. DNA, you should have, if you're doing biology, you would have gone through DNA recently. That's a polymer of nucleotides. And starch is a polymer of sugar. So a couple more examples there of naturally occurring polymers, but not made by a condensation polymerisation reaction.